Hello guys, so in this video we're going to talk about how to test whether a series converges or diverges by applying the integral test. So basically the integral test has these three conditions, which are right here. So we test to see whether it's positive over the interval n to infinity, continuous over the interval n to infinity, and decreasing over the interval n to infinity. And how do we know that? So here I'm going to leave a quick note. So note, it's positive. To test for positive, it's positive when all terms between, when it's positive when the series remains positive for all terms between n to infinity. I'll leave it as infinity. Note, it's continuous when the series has no points of discontinuity for all terms between n and infinity. And it's decreasing when the first derivative is negative. So basically we test for decreasingness whenever, just by simply taking the first derivative. So this is something that I will strongly encourage you to take notes. That way you know how to always test for continuity. There we go. So now the first step we do in step 1 is we just test for step 1. Apply the integral test conditions for the series. So we normally, for other series, we normally apply the series test conditions last, but for integral test we do it first to see if we can take the integral or not. So in this case, the series is 2 divided by n plus 7. So we know n starts at 1 according to here. So we know, and according to here. So we know that from 1, the only point where this would be negative would be anything below 7. So anytime that, and to be exact, negative 7. So anything below negative 7 will be negative. But for this case, the interval is from 1 to infinity. So since the integral is from 1 to infinity, for all points, the minimum value that can be in this series, which is 2 divided by the square root of n plus 7, which I'm going to go ahead and write down here. So 2 divided by n plus 7 inside a square root. For all terms here, the lowest value we can get whenever we plug in 1 would be 2 divided by the square root of 8, which is a positive term. So therefore, it's positive. So we can check off that condition. Now, is it continuous? I'm going to go ahead and write positive. And over here, I'm going to test if it's continuous. So how do we test for continuity? Well, at what points, we ask ourselves, at what points would this function be discontinuous? So this function would be discontinuous if n is equal to negative 7. Because when n is equal to negative 7, 2 divided by negative 7 plus 7 inside a square root is equal to 2 divided by 0. So right there we have a discontinuity. However, note that we're only looking between the interval of 1 to infinity. So therefore, this point is continuous. So it therefore does satisfy the second condition. So now we test condition 3. What's condition 3? Condition 3 is it decreasing or not? So is this function decreasing? And how do we do that? We simply just take the first derivative by simply just, we test if it's decreasing by simply taking the first derivative. So we treat this as a function of f of x. So f of x would be equal to 2 divided by x plus 7 inside a square root. And you can apply the chain rule, which I'm not going to go over how to do it because that's not the purpose of this video, to find out the integral test. But I do have a video on the chain rule, so go check it out if you don't know what I'm doing right now. So all I'm simply going to do is just take the derivative applying the chain rule. So x squared plus 7 to the 1/2 divided by 2. That's the derivative. I know I did it very fast, but that's our f of x, and our f prime of x is equal to 2 divided by 2 square root of x plus 7 negative. 2's cancel, and we're left with negative 1 divided by x plus 7. And this right here is our first derivative. And since the important part about this is that it's negative, so since we have this minus sign, we do check off condition number 3. Condition number 3 is just testing to see if it's decreasing. And this is honestly the longest part of the problem. The longest part of the problem is not doing the integral test, it's just checking to see if it meets all the conditions. So now we applied all the conditions and it does meet all the conditions of the integral test. So since it meets all the conditions of the integral test, what we're going to go ahead and do now is, since it meets the conditions of the integral test, we're going to apply this right here. So what does that mean? It means we're going to compute the integral of this function with respect to x, and depending on whether it equals a finite number or if it equals infinity, it'll converge or diverge. So if it equals a finite number or does not equal plus or minus infinity or does not exist, converges. If it does, however, equal plus or minus infinity, then it diverges. So now that we tested positivity, continuity, and decreasingness, for step 2 is we integrate series with respect to x. So now that's exactly what we're going to do right here. So the series as n starts at 1 and goes to infinity of 2 divided by n plus 7 square rooted, and is, so it turns out that I caught my mistake. So right here, the derivative of this function right here is actually not negative 2 divided by 2. It's close, but I guess I was jumping a little bit too fast. So the derivative of this function is actually negative 2, or sorry, negative 1 divided by x plus 7. Let me include that 2 in there. To the 3/2. So that's the actual derivative. The important part of this is that this is still negative. So my apologies for that. I did catch that mistake as I was looking at the problem. I questioned it. But this is the actual derivative right here. So I'm going to go ahead and put it. So I do apologize for that. But that's the derivative. But the important part is that it's still negative no matter what. So we still can integrate this. So now that we have that, we can go ahead and integrate this. So this is going to be equal to the integral of 2 divided by x plus 7 side square root times dx. So in doing so, whenever we do integrate this, we can go ahead and just pull the 2 out, which is what I'm going to do. And this is just simple. At this point, it's just simple integration. So 2 divided by 1 x plus 7 inside a square root times dx is equal to, so what we're going to do over here is we're going to apply u substitution. So our u is equal to x plus 7. Our du is equal to 1 times dx, and our dx is equal to du divided by 1. So now we can substitute this back into our function. So right here, so this is what we had. We had 2 integral from 1 to infinity, and I forgot to include that in the other. Of 1 divided by x plus 7, or divided by u, square rooted times du divided by 1. So now this is simply just the integral of 2 raised from 1 to infinity of du times du to the 1/2. And then furthermore, we can go ahead and integrate this. So the integral of 2 from 1 to infinity of the negative 1/2 times du is equal to integrate. So we add 1/2 and we divide by the same number times 2. And then this term is bounded from 1 to infinity. So the next step is we simplify the constant. So we get 1/2 times 2, we get 4. And then u to the 1/2, what was our u? Our u was x plus 7 to the 1/2. And now we simply just plug in the bounds of integration. So now from here it's simple. From here it's just integrating. So right here we get 4, we'll leave it on the outside, infinity plus 7 square rooted minus 1 plus 7 square rooted, or to the 1/2. And what does this equal? Very insignificant, because this does go to infinity. So 4 times infinity will give us infinity in this series. Since it equals infinity, what we do now is we go ahead and test or look at the conditions of the integral test, and whenever L equals positive infinity or negative infinity, then it diverges. So in this case, what is L equal to? Our L is equal to positive infinity. Therefore, this series diverges by integral tests. And that's it. Thank you for watching. I hope that was helpful. So in this video, we're going to talk about how to apply the integral test given a series. And we're going to use the integral test to determine whether the series converges or diverges. So one thing I do want you to do is I want you to take a note right here of everything I wrote down. So the integral test has three conditions where it has to be positive, continuous, and decreasing. So note that in this case that it has to be positive when the series remains positive for all terms between n and infinity. It has to be continuous when the series has no points of discontinuity for all the terms of n to infinity, and decreasing, and we can test that by testing to see if the first derivative is negative. So without further ado, we have this series right here, which is the series as n starts at 2 and goes to infinity of 6 divided by n minus 1 squared. So in this case, the first thing we're going to do for step 1 is we're going to apply the integral test conditions. And in doing so, all we're basically doing is we're just testing to see whether the conditions are met or not. So condition 1 is if it's positive. So we're going to test for positivity. If it's positive between the interval of 2 to infinity, because that is our n value. So is it positive? At what point would this function be negative? That's a good question. At no point, because the denominator is a square root, so 6 of n to anything. Now, yeah, you can make an argument saying that at 1 there's a discontinuity, but the lowest term we can have is 2, and 2 minus 1 squared is equal to 2 minus 1 is 1, 1 squared is 1. So this would be equal to 6 over 1, which is just 6. So therefore, it passes the first test of that it's positive over the interval. So now, does it pass the second test? So, I'm going to draw a line of separation. So is it continuous? Is it continuous over the interval of 2 to infinity? Now, I did mention earlier, the series is n minus 1 squared. At what point is there a discontinuity? There's a discontinuity when n equals 1. When n equals 1, 6 divided by 1 minus 1 squared is equal to 6 over 0, which is therefore equal to 6 over 0. Any constant over 0 is equal to infinity. So yes, there is a discontinuity, but that discontinuity is at n equals 1. At n equals 2, anywhere from 2 to infinity, so this is 2, infinity, anywhere right here, there's no discontinuity. And right here, I'm going to go ahead and leave a circle because there's a hole at right here. When n is equal to 1, there's a hole. So there's a discontinuity there. And everything over here on the left side is also continuous. But for the purposes of this series, it's continuous from 2 to infinity. So it does check off the second box. So it checks off condition number 2. So now does it check off condition number 3? What's condition number 3? Condition number 3 is if it's not positive, if it's decreasing. So that's condition number 3, is if it's decreasing. And how do we do that? Well, we can test for decreasing by taking the first derivative test and seeing if it's negative. So if the first derivative is negative, then we say it's decreasing. So we're going to turn this in terms of x. So 6 divided by x minus 1 squared. So what we need to do is we need to find f prime of x. And f prime of x, when we take the derivative, which we're going to quickly do by applying the chain rule. And if you don't know the chain rule, I do have a video on it, so I'm just going to fly by it. So the derivative is, I'm going to remove the constant, is 1 over u squared. G is equal to u, which is equal to x minus 1. F prime is equal to 2 divided by u to the third. And then g prime is equal to 1. And what's our u? Our u is x minus 1. So since this is a chain rule, it's f prime times g prime. So the derivative of this one would actually just be f prime times g prime, which is equal to 2 u to the third times 1, which is simply equal to 2 x minus 1. Oh yeah, by the way, that's a negative 2. Why? Because it's in the denominator. I forgot to take that into account. And very, very important. Why? Because this negative sign implies that this function, so since it's decreasing, we have checked off all 3 conditions for the interval test. So it's positive over the interval, it's decreasing, it's continuous, it's positive over the interval of 2 to infinity, because we can't get a negative, it's continuous from 2 to infinity. We found the discontinuity as n equals 1, but that's not within the bounds. And then it's decreasing since our first derivative does happen to be negative. So now that we have all 3 conditions met, the next step, step 2. Step 2 is to integrate with respect to x. So that's what we're going to go ahead and do right now. So we're going to integrate the series with respect to x. So our series as n equals 2 to infinity of 6 n minus 1 squared, we can then say that the interval from 2 to infinity of 6 divided by x minus 1 squared dx. And where am I getting this from? I'm getting this from this formula right here. So I'm going to go ahead and copy and paste this formula as well as its conditions. That way you can see exactly what's going on. So I'll paste it right over here. So right over here. So we have the integral of, so we have the integral right here of 6 divided by x minus 1 squared. And now we're simply going to apply integration. So we're going to pull the constant out, as we always do, 2 to infinity, and then we have 1 over x minus 1 squared. And I think the easiest way to go about this integral is to apply u substitution. So that's what I'm going to do over here. So I'm doing so by applying our u substitution. What is our u equal to? So right here, I'm just going to go ahead and write it. Our u is equal to x minus 1, which means our du is a derivative of x minus 1, which is simply 1 times dx. And our dx is simply equal to du divided by 1, or just du. So now that we have these terms, we're going to go ahead and substitute it back into the integral. So now that we did that, the integral of 6 to infinity of 1 over u squared times du is simply equal to the integral of 2 to infinity of u to the negative 2 times du. And whenever we integrate this, we add the power by 1, divide by the same number, multiply. We multiply by the constant, and then we're integrating this from 2 to infinity. So now we're simply going to plug in the u term. What was our u? Our u was x, according to here, our u was x minus 1. So we're going to plug it back in. So we have the integral of 6, and then we can rewrite u to the negative 1 as negative 1 divided by u. Infinity 2, so this is equal to 6 times negative 1 over x minus 1 from 2 to infinity. And now it's just a matter of plugging in the terms. So furthermore, now we just plug the terms in. So 6, and then we put in, I'll put in blue brackets, and then parentheses, negative 1 divided by infinity minus 1 minus negative 1 2 minus 1. And I'm putting parentheses around where I'm substituting the boundaries of integration for the x values. So when we do this, furthermore, we compute this, we get 6 is equal to 1 over infinity, because the 1 is very insignificant, minus negative 1 over 2 minus 1 is just 1. So whenever we compute this furthermore, we simplify this a bit further, we get 6, parentheses, 1 over infinity, this just goes to 0, minus negative 1 would be plus 1. So this is all equal to 6. And That's what our L turns out to be. So our L is just simply equal to 6. And since 6, and so now that we have our L, now the next step is to just apply. I'm going to go ahead and write it down here. Our final step is to apply the integral test conditions for convergence and divergence. So in doing so, what we're going to do is we're just going to quickly look at the conditions. Yeah, we have all this computation. Right here we have the information that matters. So our L is not equal to plus or minus infinity, and it does exist. So since that's the case, since L does not equal plus or minus infinity, then this whole series converges. By the integral test. So basically, all we did right here was, in quick retrospect, and this is our final answer. So in quick retrospect, all we did was in step 1, we're going to go over it in a nutshell to make sure it sinks in. So in step 1, we tested the 3 conditions of integration. We tested positivity, if it was positive over the interval, which it was. If it was continuous over the interval, which it was, by finding points of discontinuities to see if they were within the interval. And we tested to see if it was decreasing by taking the first derivative, which all 3 terms did work out. So then, step 2, we did some calculus, we integrated, we did some u substitution, all part of the integral, we plug in the bounds of integration, we plug in the limits, we found our L, which was equal to 6. Then from there, step 4, we applied the integral test conditions for convergence and divergence, and we found out that L does not equal plus or minus infinity, so it converges by integral test. And that's how you apply the integral test. So it's just really a matter of I think the hardest part is just applying the first 3 conditions. After that, I think it's pretty straightforward. But thank you for watching. I hope that was helpful.